So today we will try to see how the equivalent circuit parameters of a transformer can be determined by doing two simple tests. One test is called open circuit test, and in short it is referred to as OC test, and similarly there is another simple test called short circuit test or SC test. Now how these parameters can be determined, you proceed like this, that given the transformer, you connect the transformer in this way, that is, you connect an ammeter in series with the supply, then an wattmeter of appropriate rating, and then the transformer, one of the windings. Generally it is LV winding which is energized for the purpose of this open circuit test, and then there is your HV winding which is kept open circuited. One can connect, of course, across the secondary only a voltmeter to record the voltage generated. Now on the primary side you apply here rated voltage. You apply rated voltage. Let us call the LV side to be side 1 and HV side to be side 2. Then you apply rated voltage of the transformer at V1. Suppose the rating of the transformer is say 100 volt stroke 200 volt, 50 hertz, and say 5 kVA transformer. Then I will apply here 100 volt 50 hertz, okay, to the primary. Secondary is open circuited. The current drawn under this condition will be only very small. Of course, very small has got no meaning unless we specify it in terms of some other quantities. Generally, the no load current, which is denoted by I naught and comprises of magnetizing current and core loss component of current, the magnitude of that is about 5% of the rated current of that side, of the rated current. Therefore, while selecting the ammeter range, we can easily calculate from the rated current concept, take 5% of that and select the ammeter range. This will also help us to select the current coil range of the wattmeter from this knowledge of current. Pressure coil rating should be related with the voltage you are going to apply. So you accordingly set up this one. Now what you note down from this reading is the input voltage, that is V1. So readings will be readings. You remember the readings are the input voltage, the input current, that is I naught you will read, it will read I naught, and the input power, that is W naught, that is W naught. These three quantities will read. And what will be the phasor diagram under no load condition? The approximate equivalent circuit we know. So in the approximate equivalent circuit, the phasor diagram looks like this one. This impedance have been brought forward, the magnetizing branch and the core loss component of the resistance. So if I draw side by side the equivalent circuit, this is V1, this is your I naught, and this side is open, so nothing is there connected, although RE equivalent resistance and leakage reactance will be present, but this does not play any role as nothing is connected on the secondary side. So this is the equivalent circuit under open circuit condition, and this is the core loss component of resistance RCL1 and XM1. And remember that this current, two currents, breaks up into two components. One is ICL and another is IM, magnetizing component. Now, how to find out the equivalent circuit parameters? If you consider the phasor diagram here, this is the applied voltage V1. This is the no load current. I am drawing in a somewhat larger scale, I naught. This is the no load power factor angle, theta naught. And obviously, this no load current will have two components. One is this ICL component and IM component. Now, how to compute this? The computation of the equivalent circuit parameters can be done in this simple way. You first calculate the no load power factor angle, cosine theta naught, which will be, that is calculate cosine theta naught as W naught divided by B1 I naught. So that this angle is calculated, V1 and I naught. Theta naught is known. Then you can find out these two components, that is magnetizing component, by noting that this angle also will be theta naught. So then you calculate IM as your I naught sin theta naught, and ICL, which is in phase with V1, as I naught cosine theta naught. Once you get this, then the calculation of RCL, which I will write RCL1 with respect to side 1, will be simply V1 by ICL, and XM1 will be simply V1 divided by IM. So from the open circuit test, you can calculate these two parameters, RCL and XM. The parallel branch parameters of the transformer can be calculated. Only thing is, I should like to point out that while carrying out the open circuit test, it is generally recommended that you carry this test out from the low voltage side of this one. Theoretically, there is nothing wrong if you carry out the test from the HV side as well. But if the rating of the transformers are, say, of this kind, say 400 volt stroke 6000 volt, then it is better to carry out the test from the LV side, because in the laboratory you may not have this 6000 volt available, or even if it is available, it may not be very safe to operate, to carry out the test. And also, if you want to energize the winding with the rated voltage of 6000 volt, the ratings of the wattmeters, pressure coil of the wattmeter, voltmeter, etc. will also go up. So generally, LV side, from the LV side, the open circuit test is carried out, and RCL and XM is calculated with respect to that side. Then the next test is the short circuit test. During the short circuit test, what is done? This test is generally carried out from the high voltage side of the transformer. This is a high voltage side, which happens to be our side 2, which I have already marked, which is side 1, side 2, and this will be the LV side of the transformer. LV side should be shorted by a thick wire or by an ammeter of appropriate rating, whichever way you can short it, by an ammeter or a thick short circuit. On the primary side, once again, you connect an ammeter and an wattmeter here. And then don't apply rated voltage. That is very important. What you have to do, you have to make an arrangement so that you can apply variable voltage while doing the short circuit test. That is, you apply voltage through an auto transformer or a variac. This is a variac. Now, before you start doing this experiment, transformer ratings are available to you. So, you know what are the rated current of the two windings that you get by dividing the kVA with the respective voltage. So, rated current of this side is known, and we are energizing HV side. So, I can fix up what will be the rating of the ammeter. I can fix up what should be the rating of the wattmeter current coil. Now, what about the ranges of the voltmeter that I should select? This voltmeter, which I would like to measure how much voltage I am applying, and what will be the pressure coil rating of the wattmeter. These two things are to be known. Now, if you look at the circuit, the secondary is shorted. So, how the transformer equivalent circuit approximate if I draw, how it will look like during the course of the experiment? It will be this one, approximate equivalent circuit only. It will be like this. There is some total of equivalent resistance, reactance, and these 2 points are shorted. These 2 points are shorted. That is, there is no load here. Load impedance is 0. Therefore, let us imagine I have applied the full rated voltage of this HV side. Then how much will be the current? Magnitude of the current here will be limited only by the internal impedance of the transformer. That is this one. Is not? This voltage divided by this impedance will practically decide what will be the current drawn from this place. And that current will be quite large because of the fact for a good transformer we have taken care at the design stage to see that this equivalent resistance and leakage reactance are very small. Therefore, the transformer may be spoiled if proper precaution is not taken. So, what you should do during the course of the experiment, you set the variac setting at the 0 point so that you can increase the voltage from a very low value slowly. And keep an eye on your ammeter reading. You will find the rated current will start flowing at a much lower voltage because the secondary is shorted. So, go on increasing the variac setting such that rated current of this HV side now starts flowing. And you will find when this current is rated, the current in this one will be automatically rated by that transformation ratio of turns. So, anyway, so what you do is this, you apply, you write down, you apply such a voltage so that rated current flows. It has been found that this voltage comes out to be of the order of 10 to 15% of the rated voltage. Generally, these are not final thing, but it will help you to select what voltmeter I should connect here. What should be the pressure coil rating of the wattmeter? Are you getting? Generally, 10 to 15% of the rated voltage is to be applied. Maybe slightly more, slightly low, depending upon the type of the transformer. So, for example, in this case, if the transformer rating is say 100 volt stroke 200 volt transformer, and you are carrying out the test from the high voltage side, how much voltage do you expect should be applied? Say about 10% of 200, about 20 volt, maybe 30 volt, like that. So, that range is important to know before you start doing the experiment. So it will help to select that. Okay. Therefore, you go on applying the voltage such that rated current flows. Then you note down this reading, ammeter reading, which I will call it now ISC, WSC, and VSC, how much voltage you have applied. Now, what will be the equivalent circuit now? During short circuit test, if you are doing the experiment from the HV side, here there will be RCL2, here there will be XM2, and what should I write here? This resistance, what should I write? R equivalent secondary side, X equivalent secondary side. All impedances transferred to the high voltage side. I mean this side where I have applied voltage. Now here one important thing should be noted. The applied voltage being very small during the short circuit test, the flux level in the core of the transformer will be also quite small, because flux level in the core of the transformer, as I have told many a times, depends upon the applied voltage, frequency on that, ratio of that. So frequency is kept constant 50 hertz, but applied voltage is reduced to this level. Therefore, flux level too will be about 10 to 15% that of the rated flux when full voltage is applied on the core of the transformer. Now, if flux level is reduced to such an extent, then Bmax in the core too will be reduced. And as we know, eddy current and hysteresis loss, eddy current loss, for example, is proportional to Bmax squared. Eddy current loss is proportional to Bmax square, and hysteresis loss is proportional to, once again, Bmax raised to the power some 1.6 or so. Therefore, both these losses will be reduced to a very small value. And we can say that during this test, the reading of the wattmeter practically registers the power loss in this equivalent resistance. So we neglect the core losses in the transformer during the course of short circuit test. Because of what reason? Because the core loss in the transformer will become very small. But the loss here in the RE2 will be quite high, because you are passing rated current. So compared to this one, this will be quite small. Therefore, we can assume that the wattmeter, this is an assumption, of course, based on solid argument in this way, that the wattmeter will register only the copper loss. So we can approximate WSC registers the copper loss alone, copper loss. In fact, this current drawn is can be totally ignored, and this ammeter reading is this current only, because this impedance is quite high compared to these two. So this parallel branch can be neglected. So whenever possible, particularly during these two tests, you try to approximate to your advantage. I mean, this advantage, in this sense, one should look at it. For example, if I ask you to calculate, find out the equivalent resistance, I mean, going slightly away from this topic, suppose I ask you to calculate what will be the equivalent resistance of this circuit, series parallel circuit, where this is say 5 ohm, this is say 2 ohm, this is say 300 ohm. What will be your answer? Tell me quickly. 7 ohm. Because the equivalent resistance between these two will be 300 into 2 by 302. So always equivalent resistance comes out to be nearer to the lower value. So this comparison is important. So whoever calculates 300 into 2 by 300 plus 2 plus 5 is accurate, fine, no problem. But the man who will come up quickly with 7 ohm has thought the problem rather physically, what is happening, what you will do with 7 ohm or 6.99 ohm, like that. So with that spirit you have to look here while approximating things, so that it gives you really some advantage from the point of view of numerical calculations and other physical interpretation as well. Because here why you are neglecting core loss is very well founded by this physical argument. Flux level is quite small. Anyway, so after calculating this WSC, this time the calculation can be done, because these are all series parameters. So what you do is this: I can straight away write ISC square into RE2 will be equal to your this WSC, and hence RE2 can be calculated, is known, that is WSC over ISC square. And since it is a series circuit like this, JD2 can be calculated as BSC divided by ISC, and then XE2 can be separated out as equal to your ZE2 squared minus RE2 squared. So this will complete the determination of the parameters of the equivalent circuit. So you know RE2 XE2 is known, these are known, that is those parameters which comes in series with the equivalent circuit, and we have already calculated RCL, but remember it is 1, and XM1 with respect to side 1. Now the remaining part is rather important. After calculating this, what will be your objective? To draw the equivalent circuit with respect to a particular site. Then don't mix up these calculated values, because they are calculated from different sides now. Now suppose I want to draw the equivalent circuit with respect to, say, side 1. Refer to side 1. What will be my equivalent circuit? I will draw like this. This is there, RCL1, XM1. This will be there. So this is RCL1. This does not require any transformation. But here I should not put those numerical values, whatever I have got here, RE2, XE2. What should I put? That A squared thing will come, which should transform. I should write here RE1, XE1. So that I know how to transform this. And this will be the equivalent circuit referred to side 1. Similarly, while drawing the equivalent circuit referred to side 2, this RE2, XE2 will be intact there on that side, but these things will get transformed accordingly. So there you should be a bit careful before further proceeding with your calculation. Now to conclude this test, similarly I would like to tell about the open circuit test one important thing, that during open circuit test, forget about this equivalent circuit. If you look at the thing physically, during open circuit test, although I am applying rated voltage, but the current drawn will be quite small, no load current. So here also the wattmeter reading I am approximating it to what? As if it is recording only the core loss. Because of the fact this current is quite small. The copper loss, this current is passing through the winding resistance and only through the primary winding resistance, no doubt. But that power loss we neglect compared with the core loss in this case, because core loss here will be quite high. Full voltage is applied. Okay, so that is one should note, and that's why this equivalent circuit is justified. So from these two tests, the equivalent circuit parameters can be found out. Although obviously you can see that you cannot separate out the parameters. That is, when I say you get RE2, I really do not know how much is R1, how much is R2 separately. Similarly, when you calculate XC1, you do not know how much of it is XL1 and how much of it is XL2 reflected. Are you getting? Those separation cannot be done. And we are also not interested to know at this stage. Even if we know this much, we can proceed further to find out various things of a transformer related with performance of the transformer. Are you getting? The XL1, XL2 we have not separated, or R1, R2 we have not been able to separate, which comes in series. But nonetheless, we have been able to find out what is the total effect of the resistance of primary and secondary taken together and leakage reactance taken together. So what I will suggest that you solve one problem on your own by looking at any standard book where open circuit, short circuit data are given, and calculate the parameters referred to both the sides to give you a feelings of that. Now I will come to the case of the efficiency of a transformer. How to calculate efficiency of a transformer. Efficiency of any machine will be generally denoted by this letter eta, Greek letter, which, as you know, will be the, generally speaking, it will be output by input, they call it. So we will call it output power in watt or kilowatt. No question of kVA. Real power output, that is important. That is, say, some kilowatt. And total input power, that is also kilowatt. No question of kVA, etc. Don't be under the impression that efficiency will be kVA, output kVA by input kVA. It is kilowatt output. That way it is defined. Before I go to calculate or obtain an expression for the efficiency, etc., let me ask you one question. We have seen that during open circuit test, it is only the core loss which is predominant, and during short circuit test, it is the copper loss which is only the predominant thing. So these two losses will occur. Can you tell me a situation when both these losses will be at their full strength? When the transformer is fully loaded, that is, windings will carry rated current and you have applied rated voltage. So generally, when the transformer will be fully loaded, it will have both the core loss and the copper loss taking place at their rated values. And then the temperature rise of the transformer will be high, etc. I mean, it will go on. During open circuit test, it is only the core loss. During short circuit test, it is only the copper loss. Both of them acting will occur when the transformer will be loaded. And also we will show you in some other testing conditions also this can be realized, perhaps in a Sampner test like that. That let us forget it now. We will take up at a later stage. So such a thing. So in a transformer, in general, two major losses takes place. These are the most important losses. One is called the copper loss, and the other is core loss. You quickly tell me. I will take up one rating of the transformer which I have already written, say 100 volt, 200 volt, and say 5 kVA transformer. You please help me. What is the rated current of the 100 volt side? One of you calculate and tell. One of you tell. 50 ampere. And this one will be 25 ampere. Fine. These are the rated currents of the transformer. Now this transformer will be loaded by connecting some impedance on the say HV side, 200 volt side, this is 100 volt side. And here during load test you apply 100 volt, 100 volt. Initially, how do I load the transformer? Let us first understand. So what you do, you first energize the primary. You get 200 volt generated on the secondary. This switch is open. Transformer only draws the no load current. Output power is 0. Now I want to load the transformer to its full capacity. What should I do? I will close this switch and gradually vary this impedance. Impedance magnitude should be made lower or higher in order to pass more and more current. I should gradually decrease this value. So this current will increase as well as this current will be increased. Now if I connect an ammeter, if I go on decreasing the value of this impedance value, ammeter reading will go up. Where should I stop? When 25 ampere reaches, then I will say the transformer is fully loaded. Now one important thing should be understood about the power factor of the load. Now suppose while varying this Z2, I have managed to keep this cos theta of the load impedance is constant. That is, suppose you imagine your load comprises of some R and XL, and I am varying R and X in such a way that their ratios are constant. That is, theta 2 is constant. But I am varying the magnitude of the impedance Z2, and I can load the transformer 25 ampere. Now what I am trying to tell is this one, that for a given power factor, I can pass rated current by manipulating with Z2, definitely. Now cos theta could be anything. Suppose I decide cos theta is set to a very low value, 0.1, and I manipulate Z2 such that 25 ampere flows this side and 50 ampere this side. Similarly, for another power factor, say 0.8, I can also realize the same current conditions of the secondary and primary. Are you getting? Now, in both the cases, what I am trying to tell, the transformer is fully loaded. No matter whether it is delivering kilowatt, rated kilowatt output to the load or not. Transformer knows, because the moment rated current flows, copper loss inside the transformer depends upon the magnitude of the current squared into its equivalent resistance. Core loss depends upon the applied voltage and frequency, which are rated values nearly. As I told you, from no load to full load, the core loss practically remains constant. So what I mean to say that no matter whatever is the power factor of the load, if you connect such a load, even if you connect an inductive load, for example, to pass 25 ampere current on the secondary side, it is purely inductive. How much XL you should connect? 200 by that one should give 25. 8 ohm. Suppose you connect 8 ohm inductive load purely, 25 ampere will flow, and this one accordingly here 50 ampere will flow. I will say transformer is fully loaded, is loaded to its full capacity. You connect 8 ohm pure resistance, then also I will tell transformer is fully loaded. Because transformer, so far the transformer unit itself is concerned, it is carrying its rated current, because winding cross section etc. are now running to their full rating. Okay, so this you keep in mind when I calculate the efficiency of the transformer. Now that is why when we say a transformer is loaded, to what degree, we will say in terms of kVA. This point you listen carefully. Suppose I say as a general case, let S be the kVA rating of the transformer. That is, in this case, S is 5 kVA, rating of the transformer. Now refer to this transformer. If I say the transformer is loaded to half its rating, what I am trying to tell? That is, transformer is loaded such that it is handling 2.5 kVA. It has nothing to do with kilowatt. When I say transformer is loaded 75% of its rated capacity, I mean that it is loaded to deliver 5 into 0.75 kVA. So let S be the kVA rating of the transformer. It is kVA which will decide what will be the winding current, not the how much kilowatt it is delivering. That is what I am trying to tell. So S is the kVA rating of the transformer. Suppose I will use a factor X. Let S be the kVA rating of the transformer, and X be the degree of loading. Degree of loading in per unit. In per unit. Such that the general loading of the transformer, general loading of the transformer can be written as X into S kVA. I mean, very simple concept. Where X should vary between what? 0 to 1 normally. You can slightly overload it. If it is greater than 1 means transformer is overloaded. So X simply means that, nothing else. That is half loaded, 3/4 loaded, like that. So this is there. Let us also say that P core be the core loss of the transformer, be the core loss at rated voltage condition. And you just remember, this practically remains constant from no load to full load condition. This you just write down, from no load to full load. P core remains practically constant. It is constant. And let PCU be the total copper loss of the transformer. I mean, copper loss of the transformer. Total is understood. Copper loss of the transformer at rated kVA. That is, when the transformer operates at X kVA. P core is the constant core loss, remains constant. Copper loss in the transformer, what do I mean by it? It is I square RE loss. It does not matter from which side you calculate. Take the RE value of that side, multiply it with the square of the current of that side. You will get the total copper loss. And for that you need not know how much of RE1 is R1 and R2 to calculate efficiency, etc. So this copper loss at rated kVA, this will be equal to either I1 rated current squared, I1 rated current squared into RE1, and this will be same as I2 rated secondary rated current square RE2. All these things will be there. Are you getting? So this is the P core, PCU, I define it as the copper loss, which is defined at the rated condition when the transformer is handling S kVA. At that time, what is the copper loss? And as you can easily see, unlike the core loss, do the copper loss will remain constant as you change the degree of loading? Definitely not, because the magnitude of current changes. Okay. Now tell me, then what will be the expression of the copper loss at any degree of loading x into S kVA? How much should I write? So we get this one important thing. So copper loss at any loading x kVA, at that loading, it will be equal to x squared into PCU. X square into PCU will be the copper loss, where PCU is the copper loss at the rated current condition or rated kVA condition. Okay. If that be the case, then let me write down the expression for the efficiency when the transformer operates at any arbitrary loading excess kVA. Tell me what should come on the top. Output X into S, but it is kVA only, cos theta, where cos theta is the what? Power factor of the load, where cos theta is the power factor of the load. This is important. Kilowatt you have to express. Output divided by input. So input will be this output thing plus what? Losses. What are the losses? P core. It does not change. Whatever I have defined, it is P core. And plus x square PCU, where you should remember P core is constant, P copper is constant, defined at a particular load, and of course cos theta is changing with load power factor. So today we have shown that how to determine the equivalent circuit parameters and get an expression for the efficiency. In my next class I will show you how to find out the condition for maximum efficiency of the transformer.